All right, so in this video, I wanted to just introduce a couple of helpful rules about capacitors that can help you answer the types of questions that you might run into. It basically breaks down into two different cases of charging up a capacitor, and then if we want to do something to it, like change it in some way or use a dielectric or insert a dielectric between the plates. These rules will help us understand what will change about the capacitor and what won't. For today's video, I just thought that I would use the more simpler example that we're going to take the plates of the capacitor and pull them apart so that they're now twice as far apart as they were originally. So we're going to look at each case and then we'll sort of see how they compare. Now, in case one, the scenario is that we connect a capacitor to a battery to charge it. However, then we're going to disconnect the capacitor from the battery. And in this situation, it's important to understand what quantities about the capacitor can change and what quantities can't. Just to have for reference, let's just put the expression for capacitance here, that it's charge over voltage. So when we disconnect the capacitor from the battery, what can change about the battery is the voltage. The reason that the voltage can change is because the battery would have maintained the voltage between the two plates. But in absence of the battery, there really isn't anything to keep that potential difference constant. On the other hand, the charge can't change. The reason for this is that when you disconnect the plates from the battery, the charge that is on the plates now has no path to leave. The charge can't just jump off the plates. That's not going to happen. It would need to leave through the wires, but the wires are gone, and that's why the charge remains constant. So in this situation, where we think about once we've disconnected this capacitor from the battery, and now we pull the plates apart so they're twice as far apart, what's going to happen is, so the voltage, which can be related to the electric field times the distance. The electric field is related to the charge on the plates, so the electric field isn't going to change. Obviously, we're changing the distance. So our voltage will go from its original value to twice the original value because of the increased distance. What this will do will make the capacitance go from the original value to 1/2 of that value. If you look at this expression right here, you can see that a larger voltage and the same charge is going to result in a decreased capacitance. So that's all well and good. Another thing that we might be interested in is how does the energy stored in the battery, in the capacitor, change? And so I'm going to use the expression for energy of 1/2 Q times V. So originally the energy stored in the battery, I don't know why I keep saying that, in the capacitor, is going to be 1/2 the charge times the original voltage. The new energy stored, once we separate the plates, is going to be 1/2 Q naught times 2 V naught. So this is actually twice the original value. So the action of pulling the plates apart has actually increased the potential energy of the capacitor, the energy stored. One way that we could understand that is that it would actually take work to pull those plates apart because of their equal and opposite charge, they would be attracting each other. We would have to exert an external force to make that happen. And that work that we would do on the capacitor was then transferred in the form of energy into the capacitor. So that's the situation with case one. In case two, we're going to start off the same way by connecting the capacitor to our battery to charge it up. But this time we're going to keep it connected to the battery. Now, because we keep the capacitor connected to the battery, the voltage will remain the same. Regardless of what we do to the capacitor, connecting it to the battery will determine the potential difference of the capacitor, and the potential difference of the capacitor will be equal to that of the battery, and that won't change. Now, you might think, well, that doesn't really make sense because in the previous case, I saw that increasing the distance had an effect on the voltage. But remember, in that case, the electric field, which was related to the charge, couldn't change. What can change now is the charge on the plates. Because of the fact that the capacitor is still connected to the battery, there are wires connected to the plates. And those wires give the charge a place to escape or to be transferred to the plates, depending on what the case may be. So, in order to keep the voltage constant, the charge will actually have to decrease in order to maintain the same potential difference. So Q, the original charge, is going to have to become half, or the new charge after we've separated the plates will be half of its original value, and that will make the electric field half as strong, which will then allow the potential difference to remain the same even though our distance is doubled. Now, taking those two into account, because of the fact that the capacitance, how will the capacitance change, then, the capacitance will actually become half of its original value, like it did in the first example, because of the increase in the distance between the plates. Now, let's think about the energy stored. The original energy stored in this capacitor is exactly the same as case one, but now when I look at the new energy stored, in this situation, there's actually, the potential energy has actually decreased. And so this is an interesting scenario. This actually means that in that situation, it would actually become easier to separate that. That would be somewhat, could be thought of being related to, as you're separating the plates, the charge is going to be leaving the plates, given a weaker electric field and a less force of attraction. And so it's actually going to be energetically preferable for those plates to be further apart in this scenario. Another way to think about it, or just to think about potential energy in general, and we've seen this in other situations, is that a case where potential energy decreases is really sort of the preferable way for nature to proceed. Think about balls rolling down the hills. And so it's going to actually be easier in this situation to separate the plates, as opposed to case one, where it actually took external work to make that happen. Now, as I said at the beginning, we can use these rules or these key pieces of information to also understand different situations. As we move forward and look at dielectrics, that'll be a very common example that we will look at. You know, in different scenarios, if I insert a dielectric in between the plates of a capacitor, thinking about what will change on the capacitor and how that will cause a change in capacitance, because dielectrics do cause a change in capacitance. But these rules about whether the capacitor is connected to the battery or not will be helpful in understanding those scenarios.